this clip shows a character from Game of Thrones impaling a dragon with a javelin from an extremely impractical distance. To start, the current record for the fastest release velocity of a javelin was set by Roald Bradstock, who threw a 0.8 kilogram javelin with a release of 70 miles per hour, roughly 31.29 meters per second. Estimating that the dragon is approximately 2 football fields away, 182.88 meters, we can solve for the initial x velocity. Using a timer, the javelin travels for approximately 2.86 seconds. We can use a kinematic equation for just horizontal motion since we have already solved for time. If we plug in the time and distance, the calculated initial x velocity is 63.94 meters per second. Since this is a projectile, we must solve for the angular initial velocity. Using a triangle and estimating that the javelin is thrown at approximately a 60-degree angle, we come up with cosine of 60 is equal to 63.94 over the initial velocity. Solving this yields to an initial velocity of 127.88 meters per second, more than quadruple that of the human record set by Roald Bradstock.
This clip shows T'Challa, the Black Panther, get hit head-on by an African rhinoceros running at full speed, in which he survives without any major injuries. The average male adult African rhinoceros weighs around 1,600 kilograms, and their average top speed is 15.5 meters per second, which means that the force of the rhino running is 24,800 newtons per second. When T'Challa, who's standing still, gets hit by the rhinoceros running at full speed, he's taking on the brunt of its force, and for the approximate 0.1 seconds he is in contact with the rhino's head, he receives a blow of about 2,480 newtons. The force it takes to crush a human skull is about 2,300 newtons, so it would not make sense for T'Challa to be able to withstand this force and survive relatively unscathed.
In this clip, we witness Captain America catching Thor's hammer. Through research from the MCU, we discovered that his hammer has a mass of approximately 19.19 kilograms, and it has a top velocity of 344.22 meters per second. In understanding this, we can solve for the kinetic energy of the hammer when it goes towards Captain America. If we plug it into 1/2 mv squared, the formula for kinetic energy, we get a value of 1.137 times 10 to the 6th joules. From this point, if we approximate the distance it travels to be about 10 meters, we can plug in these values to find force from the formula for work. The force would be over 113,700 newtons, and the human arm can only take 4,000 newtons of force before it breaks. Even if Captain America is a superhero, this is over 29 times as much force that a typical human arm would be able to withstand.
In this clip, Spiderman is seen stopping the fall of the elevator by pulling on the elevator with his spider web. We will need to find the tension of the rope in order to see if his spider silk rope would actually be able to hold the elevator. First off, the mass of the elevator is 1,200 kilograms. There are 3 people inside the elevator, so the total combined mass of the people is 190 kilograms. Altogether, the elevator and 3 people equal 13,622 newtons. In order for the elevator to be still, its acceleration would have to be 0. So using the sum of forces equation, the total net force equals tension minus mg, which equals 0. Tension would be equal to mg, or the total mass, which is 13,622 newtons. Ultimate tensile strength measures the strength of a material in megapascals. It's the maximum tension per area of the cross-section of a cord before it breaks. If we estimate that the radius of Spider-Man's silk is about 1 millimeter, then the maximum tension would be 3,142 newtons, which is nowhere close to what the tension calculated was.
I love you, Dr. Beam.
Guys, don't you need the remote to the lab? I just found it.
We can't throw the lab without it. Get it to us fast.
The remote! We're missing the remote. You gotta check the van.
The 2018 Marvel film Ant-Man and the Wasp is a lighthearted action film that's fun for the whole family. However, it unfortunately depicts an egregious violation of the conservation of momentum. In one scene, the character Luis uses his technological advantage during a car chase, in which he opts to go small, thereby avoiding the pursuing antagonists. This would be all well and good if the car's mass were to remain unchanged and simply become more dense. However, as we see from a previous scene, Luis is able to pick up the small car with one hand, a feat far too challenging for a 1,590 kilogram muscle car. This means that we can take the mass of the small car as 35 grams, as this is the average weight of a Hot Wheels car. Were momentum to be conserved, as it always should be in polite society, then the momentum of the Hot Wheels car as Luis drives it should equal the momentum of the original 1,590 kilogram car going approximately 60 miles per hour. Using simple algebra, this would mean that the hot rod should have been launched at a remarkable 2,732,425 miles per hour, not only killing Luis instantly, but significantly